Okay, so today we're going to look at two sections. We're going to first look at section 3.7, except we're only going to do a part of section 3.7. The title of the section talks about Kramer's rule. We're actually not going to use Kramer's rule, so I'm going to change the title. We're just going to use determinants. So I'm going to call it determinants. So determinants are related to matrices, so that's why we're going to talk about it here, but we're not really going to actually use them other than showing how to get it. They have some uses. This textbook shows a couple. There's some uses in physics. I want to show you how to do it since we're talking about matrices, but then we're going to move on to the next section. So we're going to find, and we oftentimes use DET to stand for determinant. We're going to find the determinant of the matrix, first row -6, -7, second row 10, 8. So I put DET in front of it so we know we're finding the determinant, but there's a different symbol that is often used for determinant. Instead of using the square brackets around the matrix, we just use vertical bars or vertical brackets. Same numbers, same rows, same columns. But if I just put, and you'll see this on the assignment, but if we just put the vertical bars, that means we're finding the determinant. So as long as we have a 2x2 determinant like we do here, we kind of shortcut the process as opposed to a 3x3. But really, it's a little bit more complex, but we're just going to do the shortcut version for 2x2. You're going to do two basically cross products, diagonal products. So we're going to multiply that product together. So in this case, it's -6 times 8. And then to that, we're going to subtract the other product. And so the one from left to right has to go first. The upper left-hand corner to the lower right-hand corner. That has to be in front of the negative sign. And then when we do the other diagonal from lower left to upper right, so 10 and -7, that product will be subtracted from the first. So, you get -48 minus, in this case, a -70. So minus a -70 is like plus 70. So -48 plus 70, 22. So 22 is the determinant of that matrix. Just a single value, single number.
Seems so random.
Like I said, we're not going to actually show any of the uses today. I just want to show you how to do it. So if it comes up, you've at least seen it before. But that's the extent of what we're doing with determinants. So if I wanted to give you just a formula, sometimes formulas are nice, especially for your notes. What did we do? Well, the first diagonal was the A times D. That comes first. And then from it, we subtract the C times B. Like, that's your formula. That's if it's a 2x2. If we have a 3x3, I'm going to show you the process pretty quickly, and then I'm just going to instead have you find them using your calculator. Because this one takes a little bit more time. It's not terrible, but a little more. So let's jump to 4, -8, 3. -3, 2, and 6. -4, 5, and 9. So this is known as a third order determinant because it's from a 3x3 matrix. And I really have three different diagonals to do here. When I start in the upper left-hand corner, like the first one is going to be the 4 times 2 times 9. I have to multiply all three of those together. But I actually have to do other diagonals like that, in that same direction. I would have to move over to -8 and do -8 and 6, and then it kind of ends, so kind of wrap around to the -4. But instead of wrapping it around, here's kind of the way we do that. And I want you to watch this, but you're not going to have to do this by hand unless you don't have a graphing calculator and you want to do it by hand. But you're going to rewrite outside of the matrix after the determinant, I mean. Just rewrite those first two columns. You don't have to do the third one. That was a positive 2, yes, okay. 2, 5. Okay, so we rewrite those two. And now instead of, when I do my diagonal, instead of wrapping around negative 8, 6, and then come back to negative 4, I can just keep it going, if that makes sense. So that diagonal has a negative 8, a 6, and a negative 4. They all get multiplied together. First of all, that first product was 72. This product is 192. And then I have one more. I go until I've exhausted the determinant, the top row of the determinant. I did 4, I did negative 8, now I have to start with 3. So start with 3 and do that next diagonal. It would have wrapped around to negative 3 and 5, but because I wrote them off to the right, I don't have to wrap it around. So it was a 3, a negative 3, and a 5 is negative 45. Now, I would take and add, go ahead and add, find the sum of those products. We will, and up above, in that formula up above, we had to do a subtraction. That's still coming. I still have to subtract, but that's not there yet. Add the 3 products together, and we get a total of 219. At that point, we have to switch gears and do our diagonals that go the other direction. So now I have to start from the lower left and move up to the upper right, and there'll be 3 of those diagonals. I'm going to kind of put these off to the side. I could color code it, but I don't have another pen on me at the moment, so I'm going to go ahead and multiply those. So we have negative 4 and 2 and 3, which is negative 24. And then I move to the right and I do that again. So 5 times 6 times 4 is 120. And then I have one more number still in that determinant. So start at 9, negative 3, and negative 8. That gives me 216. And so I go ahead and I find the sum of those numbers. And that sum is 312. So I found my 2 sums. And so to find the actual determinant, to find my answer, I take those 2 sums and I subtract them. So back up to the idea from up above that we had to do subtraction. So we're going to take the 219, and it has to be the first one, and then from it I subtract the second one, which is the 312, to find my final answer, which is a negative 93. So negative 93 is the determinant of that. What I want to show you now is how you can do that, especially a 3 by 3. 2 by 2, it's probably faster to just do it by hand than it is to use a pull-out calculator. On that first one we did, take negative 6 times 8, take 10 times negative 7, and then subtract those 2 things. That's faster than getting out the calculator to do it. But when it comes to a 3 by 3, I don't know that it's worth doing all of those products. So I would like to show you how to use a graphing calculator to do so. So let me try to get rid of some glare here if I can. There we go, kind of. Okay. I want to point out to you, on the left side, the 4th button down, we see the 4th button says x to negative 1, but right above it in blue, it has the word matrix. I'm going to be, in this section and the next, I'm going to get kind of comfortable with using this matrix button. Because it's in blue, I first have to hit second. So choose second, and then that matrix button. Now, some of the graphing calculators were used last hour, so your screen might not be blank like mine is, so to say. Mine just has A, B, C, D, E, F, G, etc., and there's no numbers after it. If you have one that's used, yours will have dimensions written behind it, and that's okay. It's not a problem. But I have to edit first. We see there's 3 menus, names, math, and edit. I want to edit because I have to put the matrix in. So scroll over to edit, and I'm just going to choose A. You could put it in as any of these matrices, but I'm going to choose A, and I'm going to edit it. If you already had a matrix in yours, you already have numbers. That's okay. We're just going to write over top of them. But the first thing it's going to ask is the dimensions of matrix A. Well, we're going to use this last matrix I just did, the last determinant. So let's say 3 by 3. So you can hit 3 and hit enter, 3 and enter, and then it's got a 3 by 3 matrix made there. And then you simply put the numbers in. Yep. So we've got 4, negative 8, 3, they make up the first row. Negative 3, 2, 6 is the second row. I'm just using the same matrix I did over here on paper. Just putting those numbers in. Negative 4, 5, and 9. So you can put all of the numbers in, and then once you have them put in, it's important to get out of the edit menu. I'm done editing, you have to quit before you do anything else. Your mom tells you not to be a quitter, but Mr. DeBoof tells you to quit. So let's quit. Second, quit. Get out of there. Once you have it edited and you're out of there, you've quit, you're going to go back to the matrix menu. So second, matrix. But now, I want to do some math. So I'm going to go to the second menu, the one that says math. Do any of those seem like maybe they're going to help you find the determinant? Yeah, the first one says DET parentheses. That's the one I want. So I'm going to select that. Brings me back to just the original screen, the home screen, and it says determinant, but it needs to know what we're finding the determinant of. And so here we have to tell it matrix A. The way we tell it matrix A is we have to go back to the matrix menu again. Second, matrix. And now, under the names column, here's where you choose which matrix you want to find the determinant of. So I would choose A. Now it's going to tell us the determinant of matrix A. Hit enter. There's your answer, negative 93. It's the same answer that we already found. We just let the calculator do it for us.
Yeah, I know.
So you may use your graphing calculator on the homework. If it's a 2x2 matrix, I would do it by hand. It's faster. If it's 3x3, I would probably pull out the calculator because the calculator's faster.
Yeah, it is.
But if you prefer to go by hand for all of it, that's perfectly fine. So that's what I want to show from section 3.7, and that's all I'm worried about in section 3.7. There is what's called Kramer's rule. You can solve systems that way, so you're welcome to look at that, but we're not going to use it. Now, I'm going to switch over to the next section and talk about section 3.8. So 3.8 is titled Solving Systems of Equations Using Inverse Matrices. Now, if you look in this section, it's going to show you how to do inverse matrices by hand, but we're going to use the graphing calculator to help us with that, so I'm not going to show you how to do it by hand. Instead, we're going to really pretty quickly jump into how to actually solve the system. So we're doing the same type of problems that we used elimination and substitution and graphing for. This is just another way to do it. But what's nice about using matrices is when we get into bigger systems, like 3x3, and we'll do one of those, it's easy to do it on the graphing calculator, whereas by hand it's not nearly as easy. So, we're going to solve a system. Let's go with, let me choose one. We'll go negative 2x plus y equals 9. And we're going to say y plus x equals 3. I purposefully gave us a situation that we have to adjust before we're ready to do our matrices. Anybody notice what I have to adjust before I can move on? Yeah, they're not in the same order. The first one had the x term first and then the y. The second one had the y term first and then the x. So we can't have them in mismatched order. It doesn't really matter which order, technically, but because we used to have our x's first and our y's second, I definitely want to go that order. So I'm going to put them in standard form, so the x is on the left, y is on the right. I don't care about negatives or decimals, but I do care that the x terms are first and the y's are second, and that the constant is on the other side of the equation. So I'd rewrite the second one as x plus y equals 3. Okay, so I rewrote it. What we're going to do, the way we're going to use matrices here, this wouldn't be a bad substitution problem, it wouldn't be a bad elimination problem. It'd be very easy for both of those. But I'm going to show you how we can use matrices. First, you're going to make a matrix of just the coefficients. We call it the coefficient matrix. So the first equation has coefficients of -2 and +1. That's going to be the first row of my coefficient matrix. The second equation has coefficients of 1 and 1, both positive. That makes up the second row. That was actually multiplied by my variable matrix of x and y. We actually have two rows. We put x on the top, y on the bottom. That might not seem as intuitive why I did it that way. But if we think back to our matrix multiplication that we just did in the last section, we learned that we'd take rows from the first column and multiply them. They'd kind of get flipped and multiplied to this, we take the row and multiply it to the column. So -2 would get multiplied to the x, while 1 gets multiplied to the y, which makes sense up here. And then the second row, we would have had 1 times the x and 1 times the y, which makes sense also. And then that equals our answer matrix. So 9 was the answer of the first, and 3 was the answer of the second. So we have this matrix equation. I'm going to go ahead, let me call the first matrix matrix A, and I'll put it in the calculator that way. It's been multiplied by a variable matrix. I'm going to call that matrix X. When we name matrices, we use capital letters, and that equals our answer matrix, or matrix B, I'm going to call it, and I'm going to plug it in the calculator as such. If this were an algebra problem, not a matrix problem, just an algebra problem, and I wanted to solve for X, what would I do? I would divide by A. I would divide by the A, but we can't divide with matrices. Instead, we do something slightly different. We do what's called its inverse. And so I'm going to have to take the inverse of matrix A. Here's how we symbolize an inverse. I give it an exponent of -1. That's how we symbolize inverse. And so I move it over to the other side. I do its inverse. That's how I move it to the other side. And then it's multiplied by the B that was there. The inverse of A has to come first, and the B has to come second. That's very important. Now, here's where a calculator comes in play. We're going to let the calculator do all of that math. We just needed to know what to type in. So I'm going to edit matrix A, and I'll put that matrix in as matrix A. The solution matrix I'm going to put in as matrix B. I'm not going to put the x, y in there. It's going to tell me what those are. So I put in A and I put in B, and then I will type in, I'm not even going to type in x equals, I'm just going to type in inverse of A times B once I get to that point. So, let's pull out the graphing calculators. And I'm going to go back to my matrix menu. We're going to go to the matrix menu a lot. Second matrix. I need to put it in the calculator, so I'm going to go over to edit. I know I already put a matrix A in there earlier. I'm going to replace it. I'm just going to hit enter. What dimensions do I want for this matrix A? I want 2 by 2. And then put your numbers in. The first row, -2, 1. Second row, 1, 1. And then quit. Second, quit. Next, I need to also put in matrix B. So repeat, second matrix, go over to edit, but don't edit A this time, please. You don't want to get rid of what we just put in. We're going to choose B. Its dimensions, 2 by 1. If you make a mistake, and let's say I put in 1 by 2 on accident, look at it. You see that it doesn't look the way it was supposed to. So that would be a good sign that, hey, maybe you messed up your rows and columns. It was supposed to be a 2 by 1. Now it looks like how it's supposed to look. 9 for the first row and 3 for the second row. And then quit. Okay, so we've edited, we put in matrix A, we put in matrix B. So now I have to tell the calculator, we're going to take matrix A and do its inverse and then multiply that by matrix B. Unfortunately, even though there's an A, a capital A in green right above math, we don't get to use that. We have to tell it matrix A, and the way you tell it matrix A is by going back to your matrix menu. And under names, we select the A. Now it's got the brackets around it. Now it knows it's matrix A. And then I have to do its inverse. The inverse, you can see we have an exponent of -1. Here's something that's really convenient. Take a look at the button that we've been pushing to get to the matrix menu. If you don't push second, what does it say? It says x to the exponent of -1. That's how you give an exponent of -1. That's the inverse button. So I don't have to hit second, but I do hit the same button. Oh, I just hit the wrong one, sorry. Okay, I messed it up. Let me go back. Okay, let me clear, there's clear. I'll start over. Second matrix, A, inverse, there we go. Times, matrix B, second, matrix, under names, select B. So this is going to be the inverse of A, inverse of matrix A times matrix B. Hit enter. There's my answer. It's in matrix form. What number is on the top? What does the top represent? It's a -2 there. But what does that represent? Yeah, this is my variable. It's spitting out this XY matrix. So the top number is your X, the bottom number is Y. I would prefer to enter my answer as an ordered pair instead of a matrix. So I would put my answer as an ordered pair. -2 is the X, 5 was the Y. That's the answer. That's the coordinate of the intersection point. Yep, if I graphed both of those. If I would have done substitution or elimination, it would have given me the same answer. It probably, it arguably might have been faster to solve that using substitution or elimination. And I wouldn't disagree with that. But what I want to do now, and the reason, kind of the driver for why we're using matrices, is sometimes there are systems of equations that are much bigger. You may remember that we skipped section 3-4. Now I'm going to go back and be able to do some of the section 3-4 problems. For example, solve -5x plus y minus 4z is equal to 60. 2x plus 4y plus 3z is equal to -12. 6x minus 3y minus 2z is equal to -52. There is a system of equations. Do you think that you want to solve that system by graphing? How many variables are there? 3, that would be a 3-dimensional graph. Have you ever graphed in 3 dimensions? I have, and it's not necessarily a lot of fun. And we're certainly not going to talk about it in this class. So, we don't want to solve that by graphing. Our book in section 3-4 showed how you can solve these algebraically. And it's a little bit of work too. So these problems are much easier to solve with matrices. That's why we want to show matrices so we can solve problems like this. So, yeah, it's more like elimination. So, here's what we're going to do. Set up a coefficient matrix. So, the first row was -5, 1, and -4. Second row was 2, 4, and 3, and my third row was 6, and -3, and -2. Those are my coefficients. Make sure they were all the same order, x, y, z. I did verify that first, I just didn't mention it. So my variable matrix will have x on the top, y in the second row, z on the third row, and then my answer will have a 60, a -12, and a -52. So, That's when the calculator comes in play. I'll take the coefficient matrix and put it in as matrix A. It's multiplied by matrix X, and my answer is matrix B. So I'll enter the A and the B into the calculator, and then I'll tell it inverse of A times B. I'll enter that in the calculator to get my answer. So, my phone is about dead. That app drains the battery really fast, so I'm going to switch over to a graphing calculator, an actual graphing calculator, and I think I probably still have those matrices in there from last hour. So if I go to edit, matrix A, it's 3 by 3, negative 5, 1, negative 4, 2, 4, 3, 6, negative 3, negative 2. It's already there. So yours probably isn't. So then you can go put in matrix A. And then when you're done, you'll quit. Then, second matrix, edit B. It's a 3 by 1 with 60, negative 12, and negative 52. And then you're going to quit. Here's a nice little calculator hack, if you will. It took a little bit of time to go to matrix, select A, then hit inverse, then times, and go to matrix and hit B. If you scroll up, even if it's off your screen, like my screen is cleared, if I scroll up and highlight where I had typed that in before, matrix A inverse times B, and select it, it'll pull it down and I can hit enter. It's the same formula, and then I don't have to type it all in again.
There's a fireball.
Now this one has 3 answers. They are X, Y, and Z. Since you haven't done three-dimensional graphing, you probably haven't seen ordered triples before. You've seen ordered pairs, but when we have X, Y, and Z, we can write our answer as an ordered triple. Here's, well, let's see, here's what it would look like. So, my X value is negative 8, comma, your Y value is 4, comma, your Z value is negative 4. So it looks like an ordered pair, but with the third, sorry, it's not on the screen, with the third number as the Z. So negative 8, 4, negative 4. That would be your solution to that system. And that's a lot faster than any of the other ways, at least in my opinion, of solving a system like that.